Oh, we have a full room now. Go ahead, Chip.
When we were talking about what kinds of unary instructions we could make for the P2, we had all kinds of crazy ideas. The most unimplementable one was like an instruction that would find the next or the prior prime number in 32 bits.
Well, I've pressed the record button. Welcome to the second session of the Holiday Spin2 programming series with JonnyMac. We're using the encoder today. Thanks for everybody for showing up and the many new faces that are here too. It's really exciting. If you're just showing up now and you're not sure what all we're doing here, this picture shows you a pile of parts that we've actually bought off Amazon and put in a bag and then sent back out to you all. But you can also get them from Amazon on your own. And there are LEDs, an LCD, a real-time clock, an encoder, and a temperature sensor. And last week we used the LEDs. This week we're going to use the encoder, and then we're just going to keep on going until we have a neat project that we can control. And the hardware is this. The P2 Edge on a JonnyMac board, which is most easily bought in the P2 bundle. This thing right here, the developer starter bundle. Before we get started, I think this is very important. I will paste into the chat a link to JonnyMac's PayPal account so we can all make a deposit. This is very important, as I always say, because John saves us all a lot of time when we're doing a project or a product. We can use the source code, we know it works, and everyone on the forum seems to be able to help us along too. And John lives a very unsophisticated lifestyle and works for people building products a lot of times, but like the rest of us, with the COVID times, we need to always keep things funded so we can keep pressing forward. And this will help him pursue acting, electronics, buy more video gear, software, avocados, tuna salad, Japanese food, travel, movies. Those are all John's favorite things. So I'll just drop that. This page
looks a little scary, actually. It looks like I can actually buy John.
I live in Hollywood. We are for sale.
So while I relocate the chat button, John, I'm going to turn this over to you.
Okay, I will. I guess I should share my own screen then. Before we start, I just wanted to say hello, everybody, and welcome back, because there's a big crowd, and I absolutely want to thank everybody for hanging in last week. It was a long day. I was, as I told Ken earlier, I was pleasantly exhausted at the end of the last session. And I promise we won't go so long today. It's going to be nice and tidy, and it'll be an easier day. But again, I want to say thank you for everybody for coming back, for hanging in. And I got many off presentation contacts, if you will. I don't know the best way to describe that. Notes and other ways of contact from people in the group. And thank you very much for your kindness. Some people sent some very nice notes. A couple of them hit me really hard emotionally because they were so kind. And I appreciate that. So anyway, we'll get started. I'm going to share my screen so we can share a screen.
John, while you set up, I'll just let everybody know, I will go through systematically and mute people, but please do unmute yourself if you want to say anything, or of course you could just type. So spacebar is the quickest way to unmute yourself to talk.
Yeah, and please remember, I'm a pretty easy, casual guy. As you can tell, Ken was speaking to me because he knows that I had avocado and tuna salad for lunch. So if you have a question, just shout it out. That's not going to bother me or anyone else in the least. If you need to know something, I want to answer it for you now. Again, just to stay on topic to the degree we can, this is, we're talking about Spin2 for beginners. Now, because of what we're going to get into today, I want to say that Spin2 includes PASM to, because we're going to talk a little bit about assembly today. And don't be nervous about that. It's just to show you what you'll get into later. But I want you to see, as we're developing code for the rotary encoders, the various steps that you could go through. So you'll know more about rotary encoders at the end of the day than most people will ever forget. So it'll be good. All right, so I'm going to trust everybody can see my screen. I've got a slide up that says Spin2 for beginners.
Looks
Okay.
good.
All right, so here we go. Now, just because we covered so much last week, we'll do a little bit of a review. If I can get my slideshow going. There we go. So just to review the P2 processor, it is a multi-core processor. It has 8 individual 32-bit processors. We call them cogs. And the P2 can run comfortably up to 300 megahertz. Yes, it can go faster, and people do, but 300 is a nice comfortable top end for it. I tend to run my programs at 200 megahertz, but you can do what you need to do. The cogs are bigger than the P1. The cogs have an extra 2K of RAM, which give it all kinds of nice features you can deal with. The hub is gigantic compared to the P1. It has 512K of RAM. And because it's so big, there's no EEPROM that is that big. So going from P1 to P2, the design changed from using an EEPROM to do storage to a flash, which is amazingly fast. And I know that today, I mentioned a couple of times last week, I'm working with my friend John on a P1 project. And today, as I was writing code and downloading it, I found myself getting impatient with the P1, and the P1 is so much faster relative to other processors. But I'm now spoiled by the speed of the P2, and a lot of that has to do with how fast we can download to flash. The P2 has 64 I/O pins. Remember, some of them are kind of dedicated. 2 we use for programming, and we use that for debugging, serial debugging, and then 4 pins are used for the flash. The pins can be just regular old I/O pins, so tri-state I/O pins. And if you're new and you haven't heard that term, an I/O pin on a microcontroller can be in one of 3 states. That's why we call it tri-state. So it could be an input where it's looking for a signal to come in. It could be an output and low, or it could be an output and high. So those are the 3 states of a normal I/O pin. And we call it tri-states. Now, interestingly, because of the way the propeller is architected, even when the pin is in an output mode, you can use the input to look to see what's going on. Chip was actually demonstrating that yesterday a little bit. Any questions on these things? Going. Okay. We're going to blow right through this. This is from last week. Spin is a small language, really simple, easy to learn. It's bytecode interpreted. I want to clarify that just so we're clear. When you do a download to the propeller, the propeller tool or Peanut is compiling into bytecodes and downloading the bytecode. So the source that we see on screen, that's not what's going down to the propeller. It's a compiled version of that. And so then the spin interpreter that runs in a cog pulls those bytecodes out of the hub and takes them apart and does what it needs to do with them. Now, if you're using a standard compiler like FlexProp, it's actually compiling to assembly code and downloading the assembly code to the propeller. So those are doing 2 different things. In Spin, we use indenting to define program blocks or so that we can see how things going. And this is where I get really fussy about programming standards and how neat your formatting is, because I have tracked down errors in friends' source code and a few times in my own because the indenting was off. Now in Propeller Tool, Jeff does a really neat thing where he shows you the indent levels with little lines. So that helps a lot keeping things clear. And the nice thing about indenting with or defining blocks with indents is that you don't have to have curly braces or begin and end or those kind of things. So there's a lot of kind of extraneous characters used in other languages. And interestingly, the guy who invented Python he's called Guido van Rossum. And they asked him about that, and he said, you know, if you look at a professional C program, you know, that comes from a programmer who knows what he's doing or she's doing, they use nice formatting anyway, because the human eye is drawn to that. You know, we like beauty, even in software. So he thought, well, if we're doing that nice indenting anyway, we'll just get rid of the extraneous characters. So Python does that, Spin does that, it makes things very neat and tidy. As we said, it borrows elements from other languages and still has a couple of quirky operators, but every language does, so that's not any big deal. And we have this object orientation notation where, remember, your application can have a child object, and methods inside this child object are accessed by the object name dot and then the method name, and there might be parameters that go along with it. Now, what I probably didn't talk about last week is that you can also get to constants inside an object. So you can say object dot constant in the P2. Now, if you're coming from the P1, this is a change, because in the P1, you'd have to say object hash constant name. So that's a change. I bumped into that today when I was going between P1 and P2 versions of the same program. So keep that in mind. What you cannot do, though, easily or without a little work, is you can't get to a variable. So if you have an object and it has a variable in it that you want to know about, you cannot, from here, the top, you know, the parent, you can't say, oh, give me this object dot variable name. That won't work. What you have to do is write a method in the object that sends back that value. So that protects the variables inside your object. You have to be very deliberate about giving them up. Okay. Remember, this is my proselytizing about programming, so forgive me my kind of hallelujah church moments. Start with a template. It will make your life easier. For those of you that I did put the code up a little earlier today, so you should have it. I did, to follow what Jeff is doing with Propeller Tool, the new, there is a folder inside my folder called templates. Now there's just a P2 template in there, so you can put that into your templates folder that is in your user documents. Where inside your, and this is for Windows stuff, you'll have users and you'll have Propeller Tool. Underneath that, you'll have a templates folder. And so if you didn't do that last week, you can do that now. The other thing is you'll see there's a library folder. It has all of the files that we used last week, plus the ones we're going to use additionally this week. So do that, and then you have your code. So remember, start with the template. That'll keep you nice and tidy and organized. Outline your program with empty methods just so you have kind of a feel of things. Test your methods independently so that you don't have something broken and you're trying to move on. Please, please, please keep your code neat and tidy. And one of the things you'll want to do, especially as you're adopting code from other people, if you get a program from another programmer, stay with their style. It may not match yours, and you know, frankly, this agitates my ego, but if I get code from somebody else that I have to modify, I use their style, and I look for that. And do that. It'll set you apart as a programmer, especially if you're doing that in a professional environment. Document as need be. Remember, we talked about if you name things cleverly, you know, which isn't difficult to do at all, the program will kind of explain what it's doing on its own, and then any comments that you need to add are just additional information for the user or somebody else. And test, and keep testing, and go have a coffee or a soda or a glass of water, and then test again, you know, just to make sure everything's hunky-dory. In Spin2, remember when to call a method, we just put its name there and any parameters, and it jumps out, it does its thing, and it will come back to the line that follows the call. P2 methods can return no values, so they just do something and come back, or they could return a value or more. Now, I'll ask Chip to chime in. I think the practical limit on the number of return values is 16. Is that correct, Chip?
Yes, it's 16.
Yeah, which is an enormous number of return variables. It would create a very long line of code that would get a little unwieldy. So far in any of the projects that I've done, I've never returned more than 3. And even that, I was debating whether or not I should do it because it's a lot of stuff. But when you are going to return a value from a method in the P2, you have to follow the method name and parameters with a colon and then the names of your return values. That's how you tell the compiler, hey, I'm returning stuff. You have to give those things names. Now remember too, the compiler will automatically set those values to 0 for you. So you don't have to initialize your return values unless you want a non-zero initialization. But if 0 is okay for initializing, the compiler will do that for you automatically. In Spin, in your top object, I keep doing this. Hopefully everybody can see my hands. You understand what I'm talking about? If here's your application and here's an object, this is what runs. And the first method inside that code, that application runs, I always name my first method main. If you look at Chip's documentation, he uses go. You see, the compiler doesn't care. It just will run whatever it hits first. As far as control, we're going to see this a lot more today. To do looping, we use repeat, and there are various options with repeat to do what we need to do, and we can do conditional evaluations with if else, if and else, if and else, and then case. Now we used case last week, but I didn't really talk about it, so I'll talk about it a little bit more this week. Any questions? Okay. I know I bludgeon everybody with the style. You know what my thoughts are on style. I think I did make a small update to this. Keywords and method names I do in lowercase, and method names I will also put an underscore between words. So that's how I do method names. So I did this obviously for read encoder. I would put an underscore there. Constants are in uppercase, variables in lower or camel case. Remember, if you see in a program a little P underscore and then a name in one of my programs, that means that that variable is holding an address to something, which we call a pointer. With predefined values in the green DAT section, I use Pascal case, which starts with an uppercase, and then each new word gets an uppercase letter. And then again, since that's where we can easiest, well, in fact, that's really the only place to define strings in the context of Spin. I will often use S underscore so that I know if I've got a long list of names, the S underscore says, okay, that's a string, and I know what should be done with it. Again, for my programs, I use 2 spaces for indenting. And I do have independent smart tabs by section. And I believe that stuff goes along with a template. I should ask Jeff. I don't know if that's the case, but what I'll do between now and next week is I will document my smart tab settings in case you want to start with them and then experiment on your own. If you're using Propeller Tool, this smart tabs by section applies to Propeller Tool, or if you have an editor that allows you to do that. Many don't. So I'm really spoiled by that in Propeller Tool. All right, here we go. We're going to talk about quadrature encoders or rotary encoders. Has anybody used these in the past in a project? Because I can tell you probably every one of you touched one of these, if not today, within the last week. Because if you turned the volume up or down on the radio in your car, you used one of these. If you have some kind of electronic equipment that you can set a value on, it was probably one of these. They are really ubiquitous. They're everywhere, and they're very, very simple to use. So we do. So they're great to provide a value or a position. And you can also, with different approach to monitoring them, you can get speed. So I was just talking about, the car radio, your volume and tuning and motor speed. That project I'm working on with my friend John, we have a precision encoder that is coupled with the motor shaft, so we know how fast the motor is running. So with these encoders, you can see these pins here. We have a common, and then we have what are essentially two switches to ground. So these are going to be what we call active low kind of switches. And when the thing is moving, if you look at it on an oscilloscope or a logic analyzer, it's going to look like two square waves that are going to be 90 degrees out of phase. And you'll see that in a second. I have a graphic. The outputs I said are open collector, open drain, which means we want to pull up on the outside, connected to our IO pin, and then the encoder A or B line will pull that low to create the low side of that signal. It might include a button. The encoders that we have, you know, the ones in the kit, and you know, have a button, so you press down on it, and that gives you a little button switch. And you can get fancy ones. Lachlan, you know, showing us this one that he has, and oh, I don't have that on my desk. I have one that's on a board that have where you can see the picture on the screen. This shaft is kind of solid, but you'll see these encoders with more pins on them and a translucent shaft. And in that case, built in are LEDs, so you can actually light the shaft and change its colors if you have multiple LEDs. So I have I thought I had it here. Sorry, I have a module that has a Quadrature encoder on it with a translucent shaft and RGB LEDs in it, so you can change those to any color you want. And that really lends itself with the P2 because the P2 smart pins can do Quadrature encoders. You're going to find out how to do that today. And we can also do PWM for the LEDs. So with no cogs required, we can do really nice, elegant control of a very fancy RGB Quadrature encoder. All right. Any questions? I'm going to keep asking. So, although I did put water on my desk today, so my voice doesn't give out so quickly. All right, here we go. So you'll see, I was just talking about we have these A and B pins. We generally call the A pin the clock and the B pin the data. And they're just square waves when the thing is moving. And you'll see if we call this 360 degrees, this, you know, one full cycle, that's 360 degrees, you'll notice that they're 90 degrees out of phase, all right? And that's important to the way these things work. Now, if we look at the phases and analyze them very carefully, you can see that within that 360 degrees, there are 4 cycles or 4 phases, if you will. So we have here, both are at 0. In this phase, A has gone high while B is still low. In this phase, A stays high and then B goes high. And in this final phase, A goes low while B stays high. It looks a bit like binary, but if you follow the pattern, it's not. Now, all the binary values are in this cycle. It's just they're not in binary order. And the reason for that is with this mechanism, we only want one pin to change at the same time. So that is the case with the way these operate. If you analyze this, only one bit ever changes at the same time. Whereas if you do standard binary where you have 0, 0, 0, 1, okay, in that case, only one bit changed. But then you go 1, 0, now both bits changed because this one went to 0 and this one went to 1. So that's not nice. So here you'll see 0, 0, 1, 0, there's only one bit change, goes to 1, 1, there's only one bit change, and then goes to 0, 1. And this is going in one direction, and they can actually, obviously the pattern would be reversed if we were spinning the encoder the other way. So with these two signals, we can, with a little bit of code, we can tell which direction the encoder is turning. and then use that to add to a value. If we add a little more logic and we say, hey, what is the timing between the changes? We can tell how fast it's moving. Interestingly, the Propeller 2 has both of those modes built in. So I'm going to show you that. All right, let's go to a very easy way. So I'm going to show you how to write code for the rotary encoder without using smartpins so that you can play with it and you can see how it works. It'll give you an appreciation for what's inside the smartpin. And it's really easy. And then that way, if you have a project where you're using a non-parallax processor, I mean, I know you don't want to, but occasionally that happens. Well, now you'll know how to write the code for that processor. So here's the easy version. In this version, we're just going to monitor the A-pin for a change. So what we're doing is we're just constantly watching the A-pin, and if it changes, like in this case, it went from low to high, or at this case, it went from high to low. Now, what we're going to do is we're going to create a cog that is just going to sit in a really tight loop and watch the A-pin with another device, including the P2. If you wanted to, you can use a pin change interrupt. That's a little advanced, but you know, many processors like the P2 and others that support interrupts, you can trigger an interrupt on a pin change. So we could trigger the P2 if we wanted, or another processor. We could say, hey, when a pin changes state, I'm going to run and do a little bit of code. Now, what's that little bit of code that we want to do? For when we're just doing a pin as our monitor for a change, what we're going to do is when we see the a pin change, we're going to grab the value of the B pin. So A pin changes, sample the B pin. So we have them both right now. And when that happens, we're going to compare them. So here you see when A went high, B was low. And this is when we're going, you know, we're traversing across the waves this way. So this is a forward direction. And in this case, in this phase right here, A went low, and when we sample B at that time, it's high. So you'll notice that when we're going in this direction, you know, following the arrow, that A and B are not equal when the A changed. So clockwise or forward is our new A sample is not equal to our new B sample. And again, we're doing this when A changes. Okay, does that make sense to everybody? All right, and you can see here's the other direction. When we're going the other direction, when A changes, look, in this case, B was already high. And then here, when A changes again and goes low, B was already low. So when we get a change in the state of A and we look at B and it's the same, we're going in reverse or clockwise. So in that case, if we're incrementing or decrementing a value, when A changes and it's different from B, we bump the value up. When A changes and it's the same as B, sorry, then we bump the value down. And that's really simple, and anybody can do it. And now, if those of you who downloaded the code want to follow along, we're going to go look at that in the in Propeller tool or whatever tool you are using. So we're looking at program 1, Quadrature demo 1. So, buddy, let me know when you're ready to roll. And we'll go back through, since we've got, that's our first open program for today, we'll do a quick review again. Remember, I always put a header at the top of my program so you know who to blame. This is my timing things. Now, I made a bit of a change last week. This is my post-Hanukkah, post-Christmas, in the middle of Kwanzaa, pre-New Year gift to those of you using Ansi or VT100 terminal programs. I added this terminal section, so I moved my baud rate down here, and now I've added terminal types. So let me go back to the review. Remember, we have values in Spin that don't change, or any programming language for that matter, but we call them constants. Normal constants, or how we traditionally would define a constant in Spin, is we're going to give it a name. Remember, I use all uppercase, and I separate words with an underscore. and then we say equals some value. So in this case, I have this constant called clock freak, which matches one of the system variables other than the underscore, and that's where I'm setting my speed. Now I'm doing that so I can define these other speed variables. So I have ms001 is how many system ticks are in a single millisecond. So that's my clock freak divided by 1,000. So you can see it's kind of nice too. We can actually have some expressions in our constant definition. All right. And I've done the same thing for a microsecond. And you'll see we're going to actually put this to use a little later today. And I don't know if Jeff is online, but I think this is a system variable and actually, or a system value, and it should be bolded. So I'll put a note. I just noticed that should be bold because this is where I'm actually telling the propeller run at that speed. All right, so here's my constant for my baud rate. And now here's another type of constant. These are called enumerated constants. Now, you can do some fancy things with enumerated values. I don't. I always use them simply. And the way that goes like this. You start with a value. It can be any value you like, but there's a value, and then the comma separate the value from whatever number of constant names that you have. The first name in the list is going to take this value. The next name in the list is going to take this value plus 1. So they ascend up. So in this case, TPST is going to be 0 and TANSI is going to be 1, and we could have many more. There are mechanisms in Spin to change the enumeration level. So for example, if I wanted to, I can throw another number in here. This is a silly example, but it'll make me get rid of it. So if I did this, I can stick another value into the list. It will restart the values there. So if I did this, and then I said Ken, so JonnyMac would be equal to 8, and Ken would be equal to 9. Again, these are called enumerated constants. And you'll see them. I have them in a new object that we'll use, anybody that's using the Ansi terminal. So my IO pins we talked about, I also tend to mark what they're doing if I know. That's just a help to somebody else that's looking at my code. This is a reminder to myself and everybody else, but here, you know, we have encoder inputs and they are both inputs. So they're marked that way. So I've got my encoder hooked onto my board. Pin 16 is the clock wire, which, oh, the other thing too, I'm very specific about colors for wires. So if I have anything that says clock and data like this does, I use white for clock and yellow for data. And I also tend to use blue for the switches or other things that go along with those. So on my encoder, I have black for ground, red for the voltage, which goes to 3.3 volts. I have blue on the switch connector. I have yellow on the data pin and white on the clock pin. Those are my habits.
I just wanted to interject. The default terminal setting in the zip file that I downloaded was set to Ansi.
Oh,
so people try to run this right now and they're using PST, it's going to give them garbage.
Thank you. I noticed that and I thought, oh, I thought I fixed that. So yes, thank you. So if you're what Jeff is saying, sorry, Roy is saying, if you are using propeller tool like I tend to do, change T type back to PST, T_PST. Sorry about that. Thank you for bringing that up, Ryan. So fix that. But here's what that does. Well, we'll get through the program and then I'll jump out and show you what I've done to help so that everybody has the opportunity to run programs and see the same kind of thing. So again, here's a couple more enumerated constants. Now I know something about this. This is some insider baseball. I know that true is -1. So on is going to be -1, which means 0, or false is going to be 0. And in this case, I know false is 0, so I know no is going to be 0 and yes is going to be 1. And in this case, we're taking advantage of the way computer programming languages tend to behave, where they say, well, if it's not false, then we're going to consider it true. So 0 is false. So anything that's not 0 is considered true. So you'll see, you know this from last week. This is our serial I/O. This is just serial I/O that we tend to use for terminals because it has things in. And you can see I've added in a new object called Ansi. And what this will do is if you look at PST, it has lots of control codes built into it that I think actually come from the way ANSI terminals work because they have similar names. What I did was I created an object that will return the ANSI control string. So if you're using an ANSI terminal, like for example, even if you're using FlexProp on Windows, like I can do, you do have to set something in their terminal, and I will show you. But if you're using another terminal, like I tested this with Putty, and it works just fine. You know, the upshot is that you can get fancier displays, and I'll show you. So here is our little demo program. I'm going to skip over that so I can show you how to read a Quadrature encoder. So this is the simple version. Remember, the rules are we're going to wait for A to change. So when A changes, we're going to compare A to the state of B. If they're different, we're going to increment our count. If they're the same, we're going to decrement our count. That's all there is to it. This is all we're doing here is dealing with value. Now, this is a little, not too advanced, but I'm going to show you that because we don't want to miss a change, since we don't have since we're not doing interrupts in this program, or if you wanted to port this over to the P1, you could. You'd have to make a couple of changes, but without interrupts, we have to do what we call a polling kind of mode. So what we're going to do is we're going to take this method. This is all the code that does those rules right here, and we're going to run it in its own cog. So we have our program over here, and we have the encoder code, this method, running independently. Remember, with the propeller, you have 8 processors that can all run simultaneously and independently. This is a really neat thing. So we can even put spin code into its own cog and run that. We don't have to revert to assembly if we don't want to for simple things. So this is the code we're going to do. Now you'll see that this runs in a repeat loop. So you saw that last week. And you'll notice if you look through this code, there is nothing in this repeat loop that allows it to escape. So this is going to run forever. So you don't want to call this method like a regular method, because if you do, it's going to get stuck there and you'll never get out. So that's why there's 2 things that I do stylistically. You'll notice that I've put it in as a private, and that's just a color flag to me that says, hey, that's special, because you normally don't have to have private methods in your main code. And then I also put a little note over here. It says, hey, start this with Cogspin. And so there's a little support method right here called spin start, because I have 2 versions of this code. So this one starts up the spin version, and we have a variable called QE counts. That's Quadrature encoder counts. And then we have a stack. Now, this is for another day, but when we start a new spin cog, then we need to give it some space to work with, some variable space to work with, a stack. And this can get a little black magic with figuring out the proper size of the stack, but you need to have space for all of these variables and some internal working variables. I tend to start at 32, and then, you know, some of this is experience, and this might be a thing that, you know, we talked to Chip about later to, you know, to give us some guidance. That stack we need to know so that we can run another copy of the spin interpreter in a secondary processor. So we do that through this command called Cogspin. Now, this parameter is always the same. It's called new cog. Now, if you're not, sorry, so let me make a note. If you are using FlexProp and you don't have 5.04, which I think Eric put up yesterday, you need to change new cog to this cog exec new. They're the same value, but this is what we use typically for spin. You can actually use that here as well if you're using 5.03 or lower. All right, so this tells Spin to put another copy of the spin interpreter into a secondary cog and run this code. Now, this is my encoder thing, and you'll notice here's that use of the P underscore in front of a variable. That's a pointer to the variable. So that's the hub address of that variable. And so here you'll notice in the call, I have at QE counts. So the at sign gives me the location. So I'm passing the location of this variable to the background, so it knows where to put its data. And then this is part of the cog spin. This is my stack space, so I can run. Once we do that, a new spin interpreter is started in another cog, and it only runs this code. And now it's monitoring our encoder. So remember those rules. Now, because we're looking at a change in the A, so we said, hey, here's A, and we're going to look at it again. Did it change? We have to start we have to kind of prime the pump and, get this in there. So we start with this variable called last, which is the state we entered. So this is short for pin read, and we're going to read the encoder pin. So that's either going to be 1 or 0. Now we go into our loop. And at the very top, we read the pin again. And if it is different, so if what we just read is not the same as what we last read, we have a change. Since there's a change, we're going to compare the current state of A to the current state of B. So we're going to grab B and we're going to compare those two. If they are not the same, we're going to increase our counts. This plus plus counts is shorthand for counts equals counts plus 1. So it's called the pre-incrementing. So the plus plus thing, if it's on the front of a variable like that, it happens first. One of the things too that I should have pointed out, you notice what I did. It's a little convenient cheat. Counts is a variable. If you're looking at this, you say, well, wait a minute, you're saying you're going to return counts. Technically, I'm not, because this code just runs. It doesn't return anything. But remember what I said, our return variables are always pre-initialized to 0. Well, by doing that, I don't have to put a line of code in at the start of the method that says counts equals 0. The compiler has done it for me. It's just a little convenient shortcut. And now this code says the long at this address is going to get that updated value. So this is a bit of a techie way of saying QE counts equals this counts. Now we have to do it this way because we may not have direct access. And this now, if these two things are not the same, we're going to increment our counts and then change the hub. If not, we're going to decrement. So you can see this is a pre-decrement operator. So this is going to subtract counts, 1 from counts, and then it's going to write it out to whatever address we send it to. And then we're going to save what our current state is to the variable called last and do the scan again. So you probably understood this in the first 2 seconds of me talking. It takes longer to explain this than it does to understand it. It's very, very simple. So if we go up to our demo code now, Spin Start is available to run because it's not commented. So what we're going to do is the same thing we've done, in the past. We're going to wait. We're going to start the program, wait, let the terminal open up. And I'm not sure if I showed you this last week, so I'll talk about it now because I've talked about it in the language. The propeller has an internal system counter that runs at the system frequency that we can use for timing. And this is an amazing feature of the propeller, and even in high level languages. So if you see, excuse me, if you see any code that I've written and you see a T as a variable it's usually for time. So what I'm doing right here is I'm saying, grab the system counter, whatever it is now, because the system counter, which we can get with this command, it's not writable. We can only read it. We can't modify it. Now look down here at the end, we have this waitct. This is for wait for the counter to be whatever this value is. So what I've done is I've taken the current value in T and I'm adding the number of system ticks in 20 milliseconds. That's why I have this constant defined, so I can do things like this. And plus equals means add them together and put it back into T. So now when I get to this line, T is going to be 20 milliseconds ahead as far as value of where it was. What that means then is this code, all of this code, so long as it doesn't run longer than 20 milliseconds, because that's going to create a problem for us. But if it's less than 20 milliseconds, and this entire loop runs exactly every 20 milliseconds. Now for things like this, it's not too critical, but there are many, many applications where running the control loop on a very precise time schedule is really important. And the propeller makes it so easy. The project that I'm working on with my friend John, we do it just as out of habit because he does lots of video work. We're using 30 frames per second. So it's about 33 milliseconds and our loop timing is dead on that. So we're able to use that to our advantage. So what we're going to do is we're going to grab QE counts. Now you notice I've modified it. SAR is a way of dividing a number and maintaining its sign in case it was negative. And the reason I'm doing this is part of it is habit. When you do multiplication and division with a microcontroller, they're expensive in terms of code. Now in the P1, they were really expensive. In the P2, much, much less so because we have the Cortex solver for multiplying and dividing. So multiplying and dividing in the P2 is much, much faster. But if your multiplication or division is a power of 2 number, like 2, 4, 8, 16, 32, etc., if it's a power of 2, you can do it with a shift, which is a very fast way to do it. Now, when you do a left shift, which is for multiplying, the LSBN gets padded with zeros. If you do a right shift, the same thing happens. Here's the problem. If your value was negative and you do a right shift and you put a 0 over on the MSB end, you've just screwed up the sign. So SAR stands for shift arithmetic right. And what that does is it does a right shift of the value, but it puts whatever was in the original sign bit, which is bit 31, into the new place. So you maintain your sign. Now, shifting by 1 is the same as dividing by 2. Since I need a drink of water, I'm going to throw out the question. Why am I dividing my QE counts by 2? I should play the Jeopardy music. Is this thing on? Can you hear me?
Yes. Is it because you're reading 2 values for from pin A and pin B to actually have one directional value of either left or right?
It's because it's close. It's because remember in this simple mechanism we're using where we're just monitoring the A-pin for a change, there are 2 changes per cycle. So we're going to get two value changes per cycle of the encoder. And so this handles that for us. All right. Now, most of this is fancy schmancy terminal stuff, but so, you know, in my non-fancy version, we're going to just move the cursor to the home position of the screen. We're going to we're going to print it out as a decimal, and then we're going to clear anything after that. So if the value gets smaller, we do a line cleanup. That's what that's for. So if I press F10 and F12 and then enter, whoops, why is my terminal disabled? Oh, it's because, sorry, it was hiding under the pictures of all my beautiful friends. I didn't see I disabled it. So my encoder is 0. If I turn clockwise, the number goes up. If I turn counterclockwise, the number goes down. And this is really simple stuff, but again, these things are ubiquitous, and we can do all kinds of crazy stuff with them. With 2 lines and a tiny bit of code, we can change a value from anything to anything very easy. And you can see, even though I'm running spin code, I'm blasting this really quickly and it's keeping up. There's no problems. Now I'll show you this is my.
John, I have a question.
Yeah, go ahead, Ken.
So on that 20 millisecond loop, runs every 20 milliseconds, do you ever print the value of the counter to see that you're not exceeding 20 milliseconds, like with all the terminal commands?
Well, this is experience. I know that it isn't, but there have been times when, yes, I have. I have, for example, this product. I hopefully it will show. Let me put it against my shirt. This is a P1 board that I designed for EFX And on this board are 16 digital inputs that go through shift registers. And it's got a bicolor LED and a couple of other bits on there. And I run that in a background cog, just like we've done here. And I wanted to see how much work I could get done. So the other thing too is in that particular product, I wanted to have a 1 millisecond timer that I could use for timing and other things. We don't have that we don't have a get MS in the P1 like we have in the P2. So I had to synthesize it. And so what I did was I created an extra variable, and in that loop, I would grab the counter at the beginning of my code within the loop, and I would grab it at the end, and then I would print that out on my screen. And I just kept adding code to my background loop until I didn't have any more space. It is shocking, even in the P1, how much spin code you can run in a single millisecond. So I sometimes do that. I can promise you, yeah, especially when we're in Ansi mode, this is doing a lot of stuff, but we're probably only consuming 3 or 4 milliseconds, if that, in this whole loop. We could go much faster.
So the process would just be getting the new count value and then
yeah. So if I wanted, well, and here let's just.
Well, I don't want to derail you on this.
Well,
like
let's just do this. So I'm going to say TC for time check. So what I'm going to do here is I'm going to say TC.
And here's the reason I ask, because Chip always says everything is about timing. And when you can understand timing in microcontrollers, you know how things work and you can write proper code. And
he's absolutely right.
So since many of the tools today don't let you see the timing or understand it.
No, well, and Chip knows this better than any of us. Now a lot of the old timers in the forums understand this too. Back in the old days, you had to count cycles to figure out what was happening. And then if you wanted to do something really advanced, I have a friend named Jerry that I worked with at Toro who was literally a rocket scientist. In fact, those spaceship, what are they called? You know, the spaceships that have actually left our solar system and are out in deep space now? He wrote the code for those things. And, pardon?
The probes.
Voyagers.
Yes.
Voyagers,
thank you.
Voyager 2.
Yes, my friend Jerry worked on those things, wrote code for those things. And he also wrote lots of missile code and things like that. And you know, we were, then he and I were creating sprinkler timers for Toro. So that was pretty easy stuff for him. But, you know, we were using very low cost sometimes even 4-bit processors. And he would have to do all of these things where you're trying to figure out no matter what path the code takes, it runs for the same amount of time because, a sprinkler timer is a clock-oriented thing because we have time of day. We want to turn the sprinklers on at a specific time. So we have to manage all that. It gets really difficult. In the propeller, it's almost playful how easy it is. So here we'll do a quick check. Now I'm only going to check my PST code, Kim, but here I'm going to say I'm grabbing my time check. And so since I've got my thing assigned to PST, I'm just going to add here, I'm going to say term dec. Oh, let me do that. I'm going to put a character turn in here first. So this prints it on the line after my encoder value. So what I'm going to do is I'm going to grab the current value of get count minus this starting point. Which is TC. And because that's going to be in system counts and that might not be humanly fun to look at, we'll just convert it to microseconds. So from here to here, we're going to find out how many microseconds that takes. Let me make sure I'm still in PST mode because I was going to show you Ansi. Oh, there, let me put that back.
I so badly want to copy and paste off your screen.
So here's the thing. See here we're running, and you can see a couple little changes there because oh, I should probably do this. Let me do one other thing. We're going to do. I need to put clear this too, since we've got a value. All right. So now you can see, and this is in microseconds. So I've not seen it. There's the higher value. There's 63. So we're running less than a millisecond to do the work from here to here. So that's pretty fast. And I'm running the propeller too at 200 megahertz. So we could run it at 300 and it would go even faster. But this is a great tool. So here I wanted to find out how fast it was. Now, if I was really persnickety, and I am when I'm doing, client code, I would subtract out 40. I know for a fact it takes, to do the get count, it takes 40 clock ticks to do it twice. So that just fixes that. This won't make a big change in the values we see because of, 40 ticks is, a fraction of a microsecond. But there you go. So now I know that 20 milliseconds is, I could set this down to 1 millisecond and probably not have a problem. I'm not going to do that, but you see what I'm getting at.
Yeah.
So we'll do that. We could do this another time. What I've done here, doing this and this, I do all the time with the P1 and the P2. It is one of the best features about the P1 and P2 is that you can find out exactly how long a piece of code runs. And for example, when I was doing the laser tag project, that's a massive chunk of code. And I was trying to shave cycles off of everything. So remember what I said last week, give yourself permission to experiment, have fun. I will often say, okay, here's a piece of code, but I could write it this way. Well, which runs faster? I will always, I don't always choose the faster route because sometimes the slower route is a lot more elegant and might be friendlier for others. But if it's commercial code and I really need all those cycles, then I'll take the slightly less elegant looking code if it runs faster, and I can prove to myself, which does in fact run faster by using the propeller itself. It's an amazing thing.
John, can I share
Can I
really
ask a
quick
question?
well, he asked this question. I'll share the
Go ahead.
encoder in case people haven't seen it.
Somebody had a question?
Yeah, John, I'm curious, if you take your PST as you have shown it there, does your encoder have detents on it? Can you hear clicks as you turn it?
Yes.
Can you turn it one click? I want to see what the PST says for one single click.
Turn it really slowly, Ken. See, one count.
Okay, I've gotten into a situation where it would change 2 counts. It was bizarre, and I had to change the code. This one counts exactly 1 count up for 1 click.
Right. But now,
Okay.
because now you understand why, right? Internally, because in this code that we're using, we're only monitoring A for a change, and within the cycle, A changes twice. So that's why at the top of that demo loop where we have we say whatever, yeah, is it whatever my variable name is? I'm looking at my own screen, but it was is QE counts SAR1. That's dividing by 2 while maintaining the sign. In the next version, we're going to divide by 4 because we're going to do all 4 cycles.
I see. No, the way I did it was slightly different. I just waited for the pin to go high and then went and checked the state on the other one. So I didn't have to divide by 2.
Well, okay, and because you're only looking, so if you look in a 360-degree cycle, if you go look at that waveform, A only goes high one time in 360 degrees.
Right.
So yes, you would get, if you look for A to go high, well, if you look for A to go high and it has a detent, you could just count those.
Yeah.
So what you'd lose is resolution at that point. So for example, I have this encoder. I'll put it in front of my face and see it now. This is the encoder from John's project. So this one spins freely. This is an expensive device. It's a high precision decoding. Now he's put a knob on there for me for experimenting, but this encoder gets coupled to a DC motor that is running and moving things really quickly. So this is a high frequency, high precision. It runs. So here we don't do the the division thing. We want every one of those, and we'll get to that in a minute. Because what it does is by using all of the cycles that are available in those 2 waveform changes, we get the highest resolution.
Very good. Thanks.
You're welcome.
John,
Yes, ma'am.
I've had the problem that I can't get the prop plugs to actually work. I can't identify them at all in Spin. And I've changed the drivers and that. What drivers are you guys using? I'm using the prop plugs that came with the JonnyMac board.
Yeah, the
And
newer
I've tried
ones.
I've tried one of the older ones too, that are for P2s. And it's just, can't ever see it.
We'll have
Yeah.
plugged it in upside down.
Well, check that.
No.
Make sure you've got it plugged in the correct direction. You know, we've all done that. It won't, thankfully, it doesn't hurt the prop plug to do that, but make sure it's plugged in correctly. Although, here's the thing, Ken. If you plug it into the USB, your computer should still see it.
Yeah, it's not.
It's not.
Hey, Carol, I had this issue too. Make sure that you remove all of the old drivers. Go to the control panel, add remove programs, get all of the older versions of the drivers out, uninstall the prop tool, and then reinstall it, and it will install the latest ones. You probably just have too many versions of it in there and it's confused.
Okay, I have it on a separate computer where I only have the version 2.4 on it. The things I'm doing with version 1.3, I'm actually doing on a different computer.
Oh, okay.
So,
I had
and
that.
then I've also gone through and tried hand picking the driver, you know, from the Parallax drivers that are already available.
Yeah.
And I'm not sure which one to hand pick to make it work right, the ones I've tried so far.
I had troubles on Windows 10 trying to get my drivers to work initially, and I found what I needed to do is install the driver, and the minute it's done installing, plug the USB cable into the board to make sure that it gets installed. If you don't do that, it doesn't find it for some reason on Windows 10. If you're running Windows.
Yeah, I've been very lucky. I've been using 1.3. I haven't in ages, but I still have it on this computer. And, you know, I downloaded the other ones and I never did anything special. I just ran the installer and I've never had a driver problem. Now I'm running Windows 10 Professional on kind of a high power machine. I don't know if that makes a difference, but I've not had any driver trouble.
That's what I'm running on as well. And I actually contacted the company and that's what they said to do. And
Okay.
Have you checked the device manager, Carol?
Yes, that's where I'm going when I want to change. When I want to hand pick a driver, I look through the list to make sure that.
Okay, I just wanted to make sure because if the device, if it's not shown, you know, if it's X'd out in the device manager, you're not going to go anywhere.
Well, the new prop plugs I can't even find in the device manager. It shows no COM ports whatsoever. Using one of the little bit older ones that's still the blue color for the propeller one. We can find the COM port it's on, but we can't talk to it. And between Bill and I, you know, we've done this hundreds of times since the 80s. You know, I've never had this much trouble with it.
Yeah, that's surprising. I've never had trouble with it. Although, you know, some of the others have said, I mean,
Yeah,
with not with the prop plugs, but with other devices, I have either, again, through Device Manager and Windows, you can go in and check it and look for driver updates, or sometimes just cleaner to uninstall the driver and put a new version back in just to make sure everything's clean.
Well, how about towards the end if we screen share Carol's computer, and since Chip and I are here and whoever else wants to hang out, we could probably solve it.
Okay, well, right now, we're restarting the computer because the last driver we just put in.
You uninstalled it.
You uninstalled it?
I uninstalled it.
Oh, you uninstalled it. Okay.
Uninstalled it.
Okay, it asks us to restart the computer for this new driver.
Okay, well, Ken and I will show the demo so you can see what you're going to see as soon as you're talking to the
Yeah, because we're all ready to go for stuff. I've got all the stuff.
Yep. Well, and I have a demo. I have a demo today, Carol, that is just for you. Not just for you, but inspired by you.
So reboot the computer and get back online.
Yes. So let me go back to let's.
John, you could share again your screen.
Engine and motor on. Can everybody see my screen?
Yeah.
And, okay. So what I did want to talk about as well. Well, I'll just go over here. So I've got. Here is. Let me just full screen this. So this is FlexProp, and this is the program we were just running. And I've got the terminal type set to Ansi. Now, if you're using FlexProp, now I'm using the GUI when I do tests. I don't normally use FlexProp, to be honest with you, but since so many people are, I've been testing my code so that we don't have any issues. I don't want anybody to get hung up. But in here, you can go look at the commands, and somebody shared this. I think David Betts told me this, and it works. You have to have a -T at the end of your run command list. And for those of you running the command line, if you put that on, then when you do compile and run, you get the terminal, we press enter, and there is the thing. Now, though, look, we have colors. So I just did a little fancy schmancy, very little. If the number is positive, it's green. And if you go negative, it turns red. And this is ANSI control codes built in. All right. So that's where that new, for those of you that are running this, or, you know, I can go back to my own setup and do the other thing. So what I'm testing this, and I'm bringing this up just to ask my friends on, you know, that are all here, if you will check this for me, because I don't want to release this widely public, you know, put it up into the GitHub until it's fully tested by more than me. So if what I've also been doing is running a version of Putty I created, and so here we are again. So this is also ANSI compatible. So this is two different ANSI terminals I've tested it with, Putty and the terminal. I'm not sure what terminal Eric invokes for Windows, but both are working. So again, those of you that are running Ansi or VT100 terminals, I can see Dennis and David both on screen at the same time. I think you're both running Macs. I don't know what terminals you're using, but if you'd have a look at that, give it a try, the Ansi stuff a try, I'd appreciate it. I tried to ring it out over dinner a couple of nights ago. I think I caught all the gotchas in it. Oops. Sorry.
So
That was me. Sorry, I'll mute.
It's all
the
right.
FlexProp, when it runs, it invokes load P2, which does the terminal at the end after it loads the P2 code.
Is that
So
its own terminal, Roy, or is that a Windows tool? You know, something that's in Windows.
It's a terminal built into load P2.
Oh, okay,
The
it is.
code
Okay,
is in
okay,
load P2. It
okay.
does the terminal emulation. You
I
can tell
see.
it to do that or not based on the command line, right?
Okay. I was wondering how that was, because I thought it was I thought he was invoking some terminal that might have been available in Windows. I went looking for it because I ended up having to do a little bit of, I created a command line for Putty so that I don't have to start it up and tell it what I want. I just wanted to start up and do its thing like I showed. So yeah, that's why you noticed I have actually two shortcuts for Putty, one to general and one just to open up to do the demos for here. But anyway, that's what the Ansi does. I'll go back to boring monochrome just to make things easy, but that's available so that everybody should get my fancy output now. Okay, let's get back on track. So we've just seen how we could read the encoder in Spin. Now we're going to talk about assembly for a couple of minutes. Don't panic. This is really easy, you know, and if you're not interested in this, you know, assembly, go get a cup of coffee or a Coke or take a walk around the house, but it'll be here later. So 6 months from now, when you think, gosh, I really wonder what he meant about it's now, it'll be in the recording. So to start a PASM cog, it's similar. We're going to do the same thing. We're going to start by initializing our counter, that we're using our variable to 0. And then we're going to use this cog init. Now, when we're launching a PASM cog, we have many more features. I'm doing the real simple way. I'm saying cog exec new. So what this is saying, give me the next open cog and run the code inside the cog. You'll remember from the discussion last week, cogs can actually run assembly code out of the hub. We're not doing that here. This is a tiny bit of code. Look, this is the whole thing right here. It's very tiny. So we're running that out of the cog. We're going to tell it where to start running, and we're saying we have to give it a pointer, and that's pointing to this code. And then, like we did before, we're going to pass the address rather, of the variable that we want to update. So we're giving it that. So when we run this, what the Spin interpreter does is it takes this code and it sticks it into another cog and it starts running. And you're going to see this is dead identical to what we just did. So at the beginning, remember, we've got to know what A is going in. So there is a really great instruction in assembly that we didn't have before called test pin. And so that we're going to give it just a pin number. And now that's either going to be 0 or 1. And what we're going to do is we don't even need to stick it into a variable, at least not for the time being. There are 2 flags in assembly. There's the carry flag, which is called C, and there is a 0 flag, which is called Z. And this is saying, hey, look at that pin, get its level, and write it into the carry flag. So this is just a little temporary holding space for me. I'm now going to move it into a variable by saying, hey, take whatever is in C and put it in bit 0 of this variable called samples. So now I have my current state of A. And now, unlike doing it in Spin, I have to manually clear my counter. This is my counter variable. So here, move. This always made me, I thought this is a weird value. So this is saying, hey, move this value, or if this is a constant value here, it could be a variable too, but move whatever is in here into there. Now, I sometimes get a little literal in my life, so it really should be called copy, because it's making a copy of this and sticking it in that. So it's moving a copy. Anyway, this is an old mnemonic. It's been around forever and ever and ever. So now we're ready to go. So here's our whole loop. So again, we're going to look at A and put it back in C. Now what we want to do is compare it to the last. So we're going to do a thing called rotate carry left. So that's going to take our samples value and it's going to move it left by 1 bit. And whatever was in C is going to go into bit 0 of samples. And it goes into bit 0 because we shifted left. So the right side end is where we're going to put the 0. So now if we think about it in time, the old value of A is in bit 1 and the new value of B is in bit 0. So we have our 2 samples. Now here's where the magic happens in this. We talked about AND in a session a couple of months ago, but remember, AND, you have to have both values have to be 1 in order to get a 1 out of it. So if I AND samples with this constant, which is binary 1, 1, what it's going to do, the global picture is it's going to preserve whatever was in bits 1 and 0 and throw away everything else. Okay, and that's what I want to do. Now, there's a neat feature in PASM where when you have a lot of instructions, we'll do a thing where if I say, hey, write to the carry flag, what it's going to do is it's going to tell me if there was an odd number of 1s in that result or an even number of 1s in that result. It's the parity. So if I have an odd number of 1s in my result, C is going to be 1. If I have no 1s or they're both 1, so it's an even number, I have 0. So remember, to have a change, they have to be different. So what that means is if C is 1, the value changed. Now in this case, we're because of the style of the code, we're saying, hey, if there's no carry, or in this case, if there was no change, jump back to here and do it again. So this is our little monitor loop, waiting for that A-pin to change. Once it does, now we have to compare the current A to the current B. So we're going to use, this is a similar instruction, it's called test bit. It's going to grab bit 0 out of samples and put it back into C. So now the C has our last A sample, we put it back there. And now we're going to use test pin to look at the B input, and we're going to put that in the 0 flag. So now the 2 flags that we have, we can look at them. There's this really great mnemonic in Spin2 called if-diff. It means if those 2 things are different, and it doesn't care which is which, just that they're different, we're going to add to our counter. We're going to add 1. We're going to increment it. We're using adds because it's a signed value. Remember, it can go positive or negative. So adds is signed. Now, you're wondering, okay, but what if they're different? What about this? Well, the way the propeller works, if this condition fails, then this line becomes what we call a no-op. It just doesn't do anything. So it acts like it's just taking 2 cycles and nothing else is happening. So in the case where the A and B are the same, then this will run and it will subtract. So only one of these 2 lines is going to run. The other will just take a couple of cycles of time, not hurt us. And now we're going to write the long value of E counts back to the hub. When we passed, remember we passed at QE counts in the routine, that goes into a cog register called pointer A. And so we're going to write it. So this is the address then of counts in the hub. We're going to write it back, and then we're going to go back to the top and start all over. So this is the assembly version of this. You see they're both very tiny. And I wanted to go through this because now I know a lot of people in the forums have been starting to explore assembly, and this is really, really simple. Now you can see here's the spin, here's the assembly, and they are both short and small, and they work exactly the same way. And they also show some of the really nice features of Spin2 and PASM2.
JonnyMac, you ready for 2 questions?
Yes, I am.
Okay, they're in the chat. I'll read them to you. How do you know when to use a pointer versus a direct variable?
Oh.
You want to come back to that one?
That's a great question. That yeah, I'll think about it, because there are times when, yeah, I'll have to think about that, because that is one of those things where we instinctively know, and I may have to answer that next week, to be honest with you, because it's clearly going to be situational. Now, here is a case. I can't answer it here. Remember, this spin cog cannot see into the hub directly. So we have to tell it where to put that value. So we pass the address of that value to the spin cog. I was actually doing that the PASM cog cannot see directly into the hub. So the only way it can put stuff into the hub is by knowing where it is. And that comes through here. You'll often hear people use the term mailbox. This is what this is. This is our mailbox for exchanging information between the two things. Now, that doesn't mean we're limited to one value, because this is the starting address. We could have a group of values in the hub that we're dealing with that we want to go back and forth with the cog. And so this is the first one. Another really neat feature of PASM2 is that these can be indexed. So pointer 0, that's the first one. But if I had another value that came right after that, now they have to be lined up the same in the hub, I could get to that by using pointer 1 that way. It's a really great feature and saves so much setup time for assembly code. Now, to be honest with you, I deliberately crafted this code to work like this code. Now, if I wanted to be a big cheater, I could do this. I know this is called QE counts. I could do this. That would work. Now, the other thing that I could do if I wanted to add a feature to this is I could just get rid of that, and I could do this. Now, the advantage of doing this is now I can modify that, and then the encoder will update it. So if I wanted to reset it to 0, say when I press a button and I want to clear the current value, this is how I would do that. But I was deliberately doing things the way that the smartpins work so that everything would all line up.
And John, how about debouncing? Maybe I have crummy encoders, but I always have to perform some kind of debouncing. Are you using debouncing? Or are your encoders better than what Joseph has?
No, because I noticed that our kit encoders are a little noisy and do wacky things too. Really high quality encoders like this don't. You could, if you wanted to, and activate the Schmidt level. And I'm going to ask Chip to step in and help me. We could do that, right? Chip, we can enable on the pins Schmidt leveling so that we would get a little extra help when there was a state change?
Yeah, you could do that. And there are all digital filters in each smart pin. And you use the hub set instruction to configure them. I think it's hub set instruction. So they, on reset, are configured. There's 4 different ones you can choose from. One is very high speed, and it goes all the way down to like 100 milliseconds at 160 megahertz clock rate. And what these things do is they vote. Like, it wants to see unanimity out of, I think, like 3, 5, or 8 bits, and it samples at different rates. So when everything reads 1, then your output changes to 1. When all those flops read 0, your output then goes to 0.
Okay.
So
yeah.
You could select one of those preset filters, and it would digitally filter for you, and that would probably be totally sufficient and maybe better than just a Schmidt trigger.
Okay. All right. So so to your point, Ken, I noticed that because I was playing, far too late last night, but I noticed I was getting a little noise in my encoder. Now, because the encoders we have in our kits are probably mechanical switches. Device like this has optics in it, so we're getting clean outputs, and it's less problematic. So we're not using it in this code, but we could, and that just requires a little extra work. I wanted to keep this code to match our diagrams, keep it very, very simple. But as Chip was saying, you know, instead of looking for just one change, we might want to say, hey, it changed, but it needs to stay changed for a couple of checks so that we know it's really serious about its change. It wasn't just goofing off. Okay.
Thanks, John.
Any questions on the assembly stuff? I know that everybody's saying, hey, this is Spin for beginners and we're talking about assembly, but Spin includes assembly. And as you can see, and perhaps hearing me describe my own code, you know, makes it a little easier, but, you know, I want to encourage you guys to play with it. Now, I'm launching this code into a cog, but as you've seen in some of my forum examples, and Chip was doing some examples yesterday in his presentation, you can do inline assembly, so you don't have to run assembly in a cog. So that gives you the opportunity to play with it. But anyway, let's move on, because this is I thought I would be done by now. We've got a couple of things to do. Going back to the presentation. So we've done that. Now, what we were just talking about a minute ago is in this 360-degree cycle, we actually have 4 state changes if we're looking at both pins. The A pin changes state twice, and the B pin changes state twice. So we can write code that monitors both so that if either one of them changes, we're going to do something. Now, when that happens, we're going to take the current value of A and we're going to compare it to the last value of B. Remember when we were doing the previous code, it was the new A and the new B. This is the new A and the old B. So we have to save those, but you'll notice, so I've got little dots on here to show the sample point. You'll notice that the state changes where these dotted lines are. Here's where we're sampling A, and you'll notice the B sample, we're taking it from the previous check, all right? So what that means now, the rules are the same other than which we're looking at. So if the new A sample is not equal to the old B sample, then it's a positive change. And you can see that through. So when A went high here, A was high and the last B was low. In this particular case, B went high. At that point, A is still high, but remember, in the previous sample, B was still low. So those are different. That's a positive change. And now here, when the A goes low, B was still high. So and same thing here, when the B dropped, the A was low, but prior to B dropping, it was high. So that's that. And you can see the same thing happens if you look on. So the rules are the same. Now I won't drag you through all of this code. I'll just show you very quickly. If you look at program 2, the difference is we're collecting our sample, but we're grabbing both of the pins into one sample. So this, we're grabbing what's in A and we're shifting it left by 1 bit. So that goes into bit 1, and then we're grabbing B and we're putting that into last. Now we resample just like we did before. And we check to see if they're the same or different. If they're different, now the comparison takes a little bit more work. We could have done this because of just the elegance of Spin2, we could have done this slightly differently, but I wanted this to match up the assembly so that you could see how that worked, or if you had to implement this elsewhere in a non-propeller product. What we're going to do is we're going to take our last sample and we're going to shift it left by 1. So if you think about what that's doing, it's taking our old B and it's moving it into bit 1 of this variable called check. And then we're going to do an exclusive OR with the current sample. What that does is that will exclusive OR the new A with the old B. Why do we use exclusive OR? Because my uncle taught me when he was teaching me electronics when I was a youngster getting started, you know, with a regular OR, it's one or the other or both. In exclusive OR, it's one or the other, but not both. So in this case, if A is high and B is low, then we have a change. Then we know we're going positive. If A was low and B was high, that XOR result would be 1, and that also means positive. But if they're both 0 or both 1, then exclusive OR will be 0 and it's negative. So you see the same thing there. So this takes a little bit of thought, but that's how we do it. Now, since I mentioned the elegance of Spin2, we could have done this. Check equals last. So that does that shift, and then we could have said check. Oh, wait. Well, never mind. It's not as easy as I thought. Sorry, I shouldn't change my presentation on the fly. All right, we're gonna go with this. So we want to exclusive OR those 2 bits. If we get a 1, it's positive. If we get a 0, it's a negative. And you can see it takes a little bit more code in assembly to do that, but this is doing exactly the same thing. Here in this case, though, I've created a little assembly subroutine, if you will. This grabs my samples. So I'm using that test pin to grab the values. I'm clearing new scan, and then I'm putting them into the bits. So A goes into bit 1, and C goes into bit 0, and then the process is the same. We grab samples, we look to see if they changed. If they didn't, we just loop here. If they did change, this is where that XOR shenanigans takes place. And what we end up with is if this is a 1, then we know we're going positive. It's a 0, we're going negative. So we're doing the same thing here. We write it to the hub and we save our old scan information, and away we go. Easy peasy. So you could translate, in fact, this code, because it gives us more resolution, remember we're getting all 4 cycles. This is how I do it in the P1. I talked about that camera platform control project where we had 3 encoders on it. This area would grab all of the things. Now in the P1, there's a lot more work to be done because you have to create a mask for the pin and then do extra work. The PE2 is so elegant, it's crazy. This code, so this is architecturally how I do it in the P1, but there's a lot more code to set up the masks and dealing with that. But you can do it. Like I said, I've used encoders in camera control projects many, many times in the P1. Now, the great news for us though is we don't have to do this. I dragged you through all this so you could understand encoders and code them manually if you wanted to, but in the P2, we have, I'm trying to find my PowerPoint, we have smart pins. So remember, smart pins are this interesting group of logic attached to all of the pins that will handle complex tasks for us. Quadrature encoder is one of those tasks. So as you just saw, because we were wanting to do that constant monitoring of the A-pin or both pins, we had to run it in its own cog. Now, if you had another processor, or you could on the P2, I should say that those of you trying this on another processor, and I'm going to try this on the P2, you can use an interrupt. I guess I did mention interrupt. So if you have a processor capable of doing interrupts, and the P2 is, you don't have to sit looking at that pin. You can set up an interrupt so when the pin changes or either changes, you go run some code, and then the rest of the code is the same. So the smart pins though allow us to do a lot of things that we don't need a cog for anymore. For example, in the P1, I do lots of PWM stuff. Excuse me, in the P1, I have a PWM driver. I don't need that anymore in the P2 because I can use a smart pin. So there's about 31 smart pin modes. And what you're gonna, these are the commands we're gonna use. Pin start sets up the smart pin in total. And if you need to make changes to it, we can use write pin which writes the smart mode, WX pin, which writes to the smart pin's X register, we'll see that in a second, and WY pin. Now, smart pins, when you read the documentation, they also have a Z register, but that's a value you're going to get back. You can't change that. You can only read it. Now, this, I was trying to think of something clever to say, so here's what I came up with. This is the tour of the sausage factory. You don't have to remember the blood and guts and gore of the sausage factory to enjoy delicious sausage. You just enjoy the delicious sausage later. But this is the sausage factory that is nicely put into an object that we can use. So in the smart pin, we have this configuration register, and for Quadrature encoders, we're concerned with the mode bits. They're right here. And also the B pin offset bits. Remember, the Quadrature encoder has two outputs, right? So we have an A output and a B output. So for this, what we're going to do is we're going to program the smart pin that we're attaching the A output to, but that needs to know where the B pin is. Now, because there's so much cool stuff that smart pins can do, we can't actually put a full pin number in here. We can only put an offset, and we're using these 3 bits. So since we have 3 bits, we can go from -3 of our current pin all the way to +3 of our current pin. So that is a restriction, if you will. Although for Quadrature encoders, I don't find that a restriction, because in every design I've ever done with Quadrature encoders, the A and B pins are adjacent IOs. All right, so that's that. Now the mode for a Quadrature encoder is this, but you don't have to care because Chip built a nice constant into the compiler called P Quadrature. And now there are actually 2 modes. This is really cool. What we're doing with, turning the knob and getting a value out, that is called, position mode, or just absolute value mode. And it's doing what we just did in code. If you change, so that's, you set X to 0, the X smart pin register to 0. If you set it to a non-zero value, what it's going to do is it's going to measure that many system ticks, and then it will give you back how many changes happened in that period. Well, what that lets you derive is speed. And this is really nice. Again, for the project I'm trying to wrap up today with my friend John, we have this Quadrature encoder where we need to know position, because this is moving a device, but we also need to know how fast it's moving at any given time. So I had to write in Spin1 code an assembly cog that could do the normal Quadrature stuff like you saw, but also in that code I had to look for when changes happened and look at delta timing of the count register to get those changes. So it was a bit of work. It does work, but this makes it so much easier. So if we ported that project to the P2, we wouldn't need an encoder cog anymore. We would just use 2 smart pins, and the A and the B. We would set up A for our position, and we would set up the B for velocity, and we would be done. So that's how this is the stuff that we're gonna do. So I'll show you now in code. This is program 3. So those of you that haven't, if you'll look at that. Now, if you press F9 to compile that, there is an object attached called JM Quadrature. So this uses the smart pin to do Quadrature encoding. So this has a bunch of parameters that we're going to pass across, because the Quadrature encoder itself, the smart pin, the only thing that it does is give you positional values back. And you can't modify it without completely resetting it. But let me give you a real world example. If you get in the car and you turn on the radio, the volume level is going to be wherever you left it last time, even though it's not a physical potentiometer anymore. It's a rotary encoder. Well, the way that works is when you make a volume change, the software in the radio is saving that volume level to an EEPROM or a flash or some non-volatile memory, and then the next time you power up, it's stuffing that value into the encoder. And I have done that in the past with P1 encoder cogs, where I could actually tell the encoder, hey, here's your new value, deal with this. We can't do that with the smart pins. Now, that doesn't mean we can't have that functionality. We just have to work around. So you're going to see that. So the reason for all this setup is this would let you accommodate all those kind of situations where you want to start up and be at a specific level. You can all do that in one call. So here's our A and B pins. We have to have those, and they do have to be within plus or minus 3 of each other. And while I'm thinking about this, can I ask Chip a question? Do the smart pins care about the A and B pin group boundaries? For example, could I have one of my quadrature pins on pin 31 and the other on pin 32? I haven't tested. I should.
No, I don't think it matters. Oh, no, okay. Let's see. No, you can cross those boundaries.
For smart pins.
Yeah, by using the plus minus 4 or plus
Yeah.
minus 3. What is it? Plus minus 3, right?
It's plus minus 3, yes.
Yeah, you can cross those boundaries, and it even wraps around at the end, and it wraps under at the beginning.
Oh, yeah. I think that Clouseau used that feature in what he was doing with his video thing.
Yeah, and it'll
Okay.
wrap. Hey, and
Okay.
John, one thing. Do you see where you're making, you say P quadrature or? I put a little thing in the chat, P underscore filt2 underscore AB. If you put that in front of the P quad aperture, it'll put an adequate filter in there. Yes.
Okay. All right. So, well, let me,
It'll,
I can't find the chat. Well,
I can, okay, just do what you're doing and then we'll add it later.
okay. Yeah. So thanks. So that'll help with that debouncing thing, and that might make this version cleaner. Again, we're dealing with our low cost quadrature encoders here. So again, the parameters are the A and B pins. Now the button pin, since we have a button on this one, but this is a, this high-end thing, it's just an encoder, no button. So the way that I tend to write code is if you don't use something, a pin, then you set it to -1 because that's an invalid pin value. Now, remember on these encoders, every time we did a little click, if we looked at the raw value, we would get 4 counts. So this tells me I have one of those type encoders. Again, if I'm using this nice one, I would set that to false. This is the value I want to stick in. So again, if I was using this volume control for an audio project, that's, I'm going to read that out of memory and put that in. And then these are my limits. So for example, again, using the volume control, I could say, hey, always limit what I'm doing between 0 and 100%. And those can be anything, and it's plus or minus. So if you wanted to go -100 to a +100, you could do that. So there you go. Now, I tend to, with some of my objects, try to make them friendly so that they protect me from myself. So here we go. I've got a variable called diff, which is difference, and I'm subtracting A from B. And what I'm doing is checking to make sure that the pins are not the same, because remember, we do need 2 pins. You can't have A and B be the same pin. So that checks that. And then this is the absolute operator. So this will get rid of the sign, and it checks to make sure that we're within 3 pins one way or the other. And if one of those things fails, it's going to return false. And so we can, our top level code can say, oh, shoot, something went wrong. So long as everything went right, we're going to copy all of these things up to here so we can use them. And now here's pin start. This is all that stuff. Now, a couple of things are happening here. The first parameter is the pin. Now I'm using the A pin. Here's my quadrature mode. Now you remember that I had on that slide, we have to set in this B pin offset. And so we do that by taking the lower 3 bits, because those are 3 bits there of diff. And so this is telling me I just want bits 2, 0, and 1. Because this works with 2's complement numbers, this gives us the correct value. And then I'm not sure if I pointed this out, but this is 32 bits, and you can see there's 4 bits here and 4 bits here. And so that's 8. This means this is sitting on bit 24. So the way that I can position that B pin offset is by shifting it left by 24. Now in this particular case, I want to be in absolute mode. So this is my X value in pin start. This is my Y value, which is not used. So I'm just putting it to 0. So that starts the Quadrature encoder, and now it's off and running. Now, I also make sure, this is habit, this may be overdoing it, but I want to make sure that the B pin hasn't been connected to something else. So pin clear will wipe out any smart pin modes that were previously attached to it and set it to input. I do the same thing if I'm using the button pin. So you can see here that I'm checking, hey, if it's greater than or equal to 0, then it's a valid pin. And if that's the case, I will clear it so that we can cleanly use its input. This D4X says, hey, it's a detented encoder. So we want to do the the multiplication by 4. So I'm using the ternary operator to change any non-zero value. This will evaluate as true. If it's not 0, I will change it to 2. Because remember, if I do an arithmetic shift or a regular shift, by 2, it means 4. It's multiplying or dividing by 4. If this is false, then it's 0. So I'll get the raw value. So again, if I'm using one of these nice fancy encoders, I get no change. Now, because sometimes we aren't thinking, and you can pass your high and low limits, and since they could be negative values and people might missee the magnitude, all this does is makes sure that the low limit is lower than the high limit. And so that's a private method down here. So you can say if low limit is greater than the high limit, that's a problem. So this is a neat bit of code where I'm swapping these two values by doing this multi-assignment. So what happens, you can see, is low limit comma high limit is assigned to high low. So you can see it's just flopping them around. So high goes into low, low goes into high. So this is a really easy way to swap two variables without needing another. All right, and finally, we're going to set the value into our encoder because we might have a preset. So I'm just going to go through these in order really quickly. Unless there's a question.
I have a question.
Yes, sir.
Can you back up to the top? How did the fixed limits get to the two values, low and high?
Oh, well, because this long move took everything from here and put it there.
My mistake. Thank you.
Because no worries. Because I am gonna change some of these things. I'm gonna convert. This could be true or false. I'm gonna convert that to 2 or 0, and I might need to swap these. And this will start as false. That's actually not a part of that group of 7. And I'm going to set it to true so that I know that I've configured the pin. So I do this with a lot of things. I have a clear routine that just means set it to 0. So you can see that's going to call this set value to 0. Now here's how, you remember I said a minute ago, you can't modify the value inside the encoder smart pin. And what I mean by that is you can't change it to a specific value other than 0. And the way that you do that is you actually reset the smart pin. So when we configure a smart pin like this, the smart pins take over some of the circuitry. So we're actually using the direction bit to turn the smart pin on and off. So if you look inside the assembly code in the interpreter, you'll see at the end of pin start, it actually drives this pin low. But since it's a smart pin, that's not making it an output low, it's turning on the smart pin circuitry. So if we want to turn off that and reset the value, we can do pin float. So by doing pin float of our pin, that's why we save that pin number, that resets and it clears the internal value. And then we can turn it back on by doing pin low. Here's the thing, we might want to preset to a specific value. So what we're going to do is we're going to take that value and we're going to make sure it's inside our limits. We're going to truncate it inside our limits. I don't know if I showed you guys this last week, but This is the min operator and this is the max operator. Now, it sounds funny to call them that because this operator is going to give the highest value of these two things. And this operator, this one here, is going to give the lowest value of these two things. I do it stylistically this way because it tells my eyes visually, I want this value to be in between this and that. You don't have to do it this way, but visually it makes sense to me. And then we put that in a preset. So this just makes sure that if our limits say were 10 to 20 and we did a preset of -5, it would actually change our preset to 10 so it fits inside the limits we've already defined. And so, just so that we can check, we pass that back. So we're going to save it for future use in this variable called offset, which is a global variable. So we're going to save that because we need it later. And then we're going to pass it back to the user so that they can confirm what the current level is inside the encoder. Now, because our ranging and everything happens outside, we can arbitrarily set that too. So this moves, this does a similar thing to what we just did above. We're just going to grab our low and high, our new low and high, and copy them to our global variables and then just make sure they're in good shape. And then we're going to reset our system by grabbing the value. And again, these are things that are all, they seem redundant, but these are situational things. I think, yeah, sometimes I need to be able to change everything at one time. We're going to do that next week, actually. So this call just sets the range and the value all in one shot. So just a convenience thing. Here's where the real work happens. So when we read the encoder, it's going to give us the internals from the smart pin. So we're going to grab that with this method called raw, which is a private method, so we can't see that outside. So it's going to use this function called read pin. This is grabbing the Z register out of the smart pin. This is the current internal value of the smart pin. And you remember, if we've defined it as one of those clicky things, then we're going to adjust it with this. If that's 0, we'll just get the raw value back. So now we know what's inside the encoder, and we're going to add that to our offset. So now that's our preset. So now our value to the outside world is in sync, or it could be in sync. We got to check it, because remember, there's no limitation inside the smart pin. So we look at this result, and if it fell below our low limit, we reset the smart pin to our low limit. If it went above our high limit, then we reset the smart pin to our high limit, and everything works out nicely. So you'll see in our example, in one of the examples, you can turn it and then you get to a level and you just keep going and the value does not change. This code is what's doing that. Ken was talking about debouncing. I'm going to have to reconsider this after what Chip was saying. This is really kind of old school debouncing, but since we have a button on these clicky things, this check press, I won't, well, I'll go, it's quick, so I'll go through it. This says, hey, look to see if the button is pressed for at least that many milliseconds. So if we're using a pin, then we're going to check to see if it's pressed. So we have to be pressed going into this routine. We're not waiting around for a press. If it is, then we'll wait for a millisecond, and then we'll increment our timer variable and make sure and check to see if it matches our time. If that's the case, we know we have a debounced button and we return true. If it failed along the way, we just had a glitch input or it wasn't pressed going in, we'll return false. Now on the other side of that, we may want to make sure that we've released the button. Sometimes, you know, like for example, on at least on Windows, I don't know if other operating systems do this, but oftentimes when you click, you click on a button, nothing happens till you release. And in fact, sometimes if you click on something on screen and then hold the mouse button down and drag and release, it doesn't do it because it's looking for the release event on top of that. In this case, this is where we're looking for a release event, if not the release event, but to make sure that the button is not cleared. That way we don't have something happening too quickly. We want to say, hey, press a button, let it go, and then we'll do something. So it prevents things from getting run away. So this is all of the code now, and we can do functional things. What I'm trying to do is I can't see all the tabs now on my, Ken, is there a way that I can move this toolbar for zoom down or away?
I'm not sure.
All right, let me see if I can see. Well, let me do this. Let me just minimize this and do it that way. See, I couldn't see my tabs. So let me go. So Quadrature encoder number 3. This is using now our Quadrature object. So if I press F10 and F12, so here we go. And this is, you know, reading a value and doing a thing and telling me I press the button. Very easy. But here's where, remember, we talked about limits. So if you look in the code, I've set my low to -100 and my high to +100. So if I go back to PST, if I keep turning this, you see, I'm still turning the knob, and yet it's not going, if I'm counterclockwise, it's stopping at -100 because that's the low limit. And I could do the same thing on the other side. So I stop at 100. So that's what that code was doing, is internally the counter wants to go past 100, but we say, hey, we're done. So we reset the thing and adjust our offset value, and we create this ability to have limits in there. Now we can change those on the fly. So for example, I'm set to 100 right now. If I press the lowercase r on my keyboard, watch what happens. It changed to 50. Now, the reason that happened, if you look in the code, I'm scanning the keyboard and I say, if I press a lowercase r, change the encoder range to -50 to +50. So I've shrunk that range. Well, what that means then, if our current value was outside the range, we have to force it back in. So you saw it went from 100 down to 50 because 50 is the new top end range. Again, if I go back to PST, I can turn, oops, I gotta turn it on. I can turn and it doesn't change. Now, if I do an uppercase R, then it frees it back up and I can go. And if I press X, it will clear that. So these are, encoders are, like I said, are very simple and ubiquitous, but these are the kinds of tools that I've actually put to use in commercial programs. Any questions on what we're doing? So you can see the codes. We started, I won't go through all this screen formatting stuff, but you know, we started it with, so just to be kind, so here are I added the button input pin, and I added my constants for my high and low value. In most programs, the range won't change. But there might be a change. There was a guy, the first time I wrote about encoders for nuts and bolts, I got a message from a guy in Miami who called himself Wayne the Brain. And it just made me laugh because, you know, I mean, I have a huge ego. I'd never call myself, you know, Johnny the Magnificent or anything silly like that. But he called himself Wayne the Brain. And he was a recording engineer. And well, I'm an actor and I know friends in the music industry. In fact, all of you old timers like me probably know the song Brick House by the Commodores. That was written by a friend of mine. She lives in a big mansion over in Beverly Hills and it has a gigantic brass plate on the outside that says The Brick House. It's hilarious. But anyway, the music industry is a really kooky industry. So I gave him my number and he called me up and he said that he was creating a timer for a project and he had multiple parameters in there. He did something that I honestly hadn't thought about doing. he had one encoder, and when he set a parameter on an LCD, then he pressed a button and it would go to the next parameter. So what he would do is he would restart the cog for the next parameter with the configuration required for that. It was really clever. I had not thought about it. And so that's why I have these reconfiguration details built in, because you might just have one encoder with a button on a device and you can use it to do multiple things. We're going to explore that next week once we hook up our LCD display. Okay, so for those of you that are doing Christmas lights, here's where we can put that to use. This is program 4. Now I've set mine up for, oops, this is, maybe I didn't do that. Let me see. Oh, sorry, I grabbed the wrong, here, the Pix. So the program that's called Encoder Pixel Demo. What I did with this one is of course, I took the Pixel demo from last week with the menu and I added the encoder feature, and instead of this, instead of displaying this menu, which I guess I should have taken out of the program because we're not using this anymore. I guess maybe I left it in for reference. What we're doing is displaying on the screen what we want to run, and as we turn the encoder, that changes. Now this is kind of boring on a screen, but once we have an LCD, this will make more sense. So if I run this program, so now as I turn the encoder, you can see that it's selecting those things that we had. You can see there's a little bit of glitchiness because of this inexpensive encoder, but here I have my limits set, so that's what I had in the menu. Now if I press a let's see, I've got things going now. Now what I did here is this little arrow says, hey, that's running, and since it's running, I need to turn it off in order to get back to my selection mode. So I press the button again, you'll see that goes away. And now I can go back to selecting. So if we look at this code, we've set up the encoder and we start, we make sure that it's clear so that everything's at 0. We call this method called show item, which shows us the 0th item from our list. That's down here. So this will show what we're currently sitting on, what selection we're currently sitting on. And, a couple of things you'll notice in here, I added some spaces up in the front so that I have room for that arrow. And you'll notice too, lights out is my longest one. So I just added one extra space and then I space padded these all out. That way, every time I display something new, it cleans up the line automatically. We don't have to do any extra work. So that's just an easy kind of thing. So here's our main loop. And what it does is it looks at the encoder and asks, did that change? If it did, then we show the new item and we save the current scan for the next scan. And now we look at the button and say, was it pressed? If it was, then we wait for it to be released. See, if we didn't have that in there, the thing would just be cycling really fast because the P2 is so fast. So this forces us to press the button, and then this if we press a button, I should say, this forces us to release it. And once we've done, we show selected. That's what puts that little arrow on the screen. It says, hey, that's what we're doing right now. And then it calls the function. So these were, you saw these last time, these were embedded in those if-then statements. And I talked about case out in the presentation, but I don't know if I talked about this next week. You can see, especially for one-liners like this, we're doing one thing, it's a much more elegant way of doing this. I replaced all those if statements with this, made it much, much easier. And we could do that even with the keyboard input. Now, Spin2 has this thing called case fast. And I do want to ask Chip a question. I know for case fast, all of these have to be contiguous, right? But do they have to begin with 0? Can I use case fast with any beginning number?
Yeah, it can be any number, and I don't think they need to be contiguous. They all just have to be bound by a range. They can't be more than 255 apart from each other.
Oh, okay. Well, then never mind. Okay, so this is just, this will speed things up if you do.
It is most memory efficient if they are contiguous values, because that does create a table at compile time, you know, for quick runtime access. So if they're contiguous, the whole thing's more memory efficient.
Okay, and you see this value here is the value right out of the encoder. You see up here where we redefined our encoder bits, here's our encoder range is 0 to 6, because that's what we have. We have 7 things in our menu, and so we matched those up. And then there's just a little bit of support code to put that onto the screen. So here is my challenge. Now, I do want to say, and I need to give credit where it's due. Hopefully he's still with us, but Kevin, our young friend who's joined the group recently, he got a P2 kit yesterday, and within 20 minutes had already started modifying my examples from last week. And kind of showed Ken who's the boss when it comes to hex, because Kevin pointed out, as I did, hey, John only had a couple of colors in here, and he wanted blue. So Kevin added blue to his string. So that was one of my challenges that Kevin met, you know, add colors and get things going. So here's my challenge to the group. One of the things that you'll notice about this is that we go up to 6 and stop. And then let me re-enable. And we can rotate back to 0 and stop. Wouldn't it be nice, especially if this was a much longer menu, if we could go from 6 and go forward to 0, a rollover, or be at 0 and go back and roll up to 6? So my challenge is that you do that this week, and then next week we'll talk about it. All right, and that's all I'm going to say on that. Is there any questions on how we stuck the encoder into this menu selection? So we did it. We took before where we were doing discrete key presses, and now we've used the encoder. Now it seems silly because we're using the terminal, but remember we're doing things incrementally, and next week we're going to have an LCD display, so we're not going to use the terminal anymore. We're going to use the LCD display, so it'll be much more like a commercial product, like a radio in the car. It has a display on it. We have knobs. We're going to do that. But I wanted to build one piece at a time. Any questions?
Yeah, I do.
Yes, ma'am.
I'm trying to think now how to word it. The clickboards, are they compatible with the propeller too?
Yes.
Oh, that's right, because we have clipboard adapters up the yin yang. I've got tons of them.
Yeah, and they're just circuits. They're compatible with anything. In fact,
yeah, what I was thinking of was because the clipboard has like an OLED screen and all of that.
Yeah, I have one. I'm writing code for it. I haven't finished it yet, but I'm close. Yeah, so any kind of display. Again, we use a terminal for development. It's easy, but later we'll use the LCD, those are ubiquitous and inexpensive.
And those are all the things I want to get going, but so far I haven't been able to talk to my boards.
Once you do, you'll fly. So now let me, Carol, since you're talking, I'm going to show you what I did for you and for Ken.
But for me,
you had mentioned using processing with the propeller in one of the presentations, and then Ken threw out a thing in the forums. And I have been interested in processing, and I'd seen it in the past. So now I'm going to confess I have about 25 or 30 minutes total time with processing. I was still able to make it work. So here's a program for everybody has that uses the encoder to talk to processing. Now it's stupid simple. Here's what happens. I check the encoder, and if it went in a positive direction, I transmit a plus. If it went in a negative direction, I transmit a minus. If I press the button on the encoder, I transmit an asterisk. That's the only thing this program does. Now I want to show you a couple of cool things about Spin2 that are in here. Here's, again, one of those multi-assignment things. Remember I told you that our local variables in methods, you're not guaranteed any value in there. You do need to manually initialize those. Now, this variable called now is going to get, I don't need to initialize that to anything, but these things I do. So remember T I use for my loop timing. So if I look down here, I'm going to run a 25 millisecond loop on this. That way I'm not jamming too many serial characters out if I'm doing things crazily. Then I have this thing called DC timer. What you're going to see is that when I press the button, that's going to do a direction or an orientation change. You'll see what I'm talking about in a minute. So that's what that is. And then I have our last. We need to pre-initialize our sampling. But I'm grabbing these three variables are getting assigned to these. And look, the assignments, they don't care if over here are variables. They can be methods or commands. So here's a command. So I'm getting the system counter and putting it into T. I'm grabbing the current value of milliseconds and putting it into DC timer. So for those of you that have some experience with the Arduino ecosystem, getMS is the same as millis. And then the encoder value is, you've seen that. That's from our encoder project. And so I'm in one nice tidy line of code. So long as I don't get too crazy with line length, this is okay for me. It's nice and easy to read, and I take care of everything all in one fell swoop. So that's a real nice add to
Well, using the comma delineators up here is kind of what sets the format of the data stream, and that way the processing program can pick up many different kinds of information.
You're right.
Off of one data stream.
In my case, I'm only sending 1 byte at a time. I'm keeping it really, really simple. Remember, I'm an actor. I live in Hollywood. I got to keep things simple. So here's what we're doing. We read the encoder. If it changed, we're going to look at how it changed. If our current thing is greater than our last, we send a positive. Otherwise, if it's less, we send a negative, and then we just save that. If the button was pressed for 10 milliseconds, then what we're going to do is we're going to grab, this is another timing check. We don't want to be able to change the direction or the orientation of this thing you're going to see in a minute too quickly. So I'm going to reuse now, because this is kind of a scratch variable in this program. I'm going to grab the current value of the system milliseconds. And what I'm going to do is I'm going to subtract the last value from that. And if it's greater than this threshold that I've set to 250 milliseconds, then I will transmit that character and I'll reset my timer window. So this kind of differential timing with the milliseconds is very common in the Arduino world, and we can do that in the propeller world. We also have the higher resolution of the system counter. The difference is at 200 megahertz, the system counter is going to roll over about 20 some odd seconds, I think it is. Now, it doesn't matter the system counter because this is in milliseconds. The milliseconds timer is going to roll over every 49 days. So we got lots of time with the milliseconds timer. So yeah, I'm doing two different time things here. I'm running this loop every 25 milliseconds, and I'm also making sure that I don't press that button more than 4 times a second. So this is just, and you see, I don't have any terminal stuff built into this. It's just sending data out the serial port. And so if I pull up processing, now forgive me for those of you that are expert processing programmers. I'm brand new, so I did the best that I could in the short time that I had with this. But this is my processing program that I have what I'm calling a robot. It's the simplest robot you've ever seen. So this is its size, and then this is its movement change, and this is its orientation. In processing, I'm saying, hey, I want to use serial. I'm starting my robot, or this is my position value for my robot, and this is its initial orientation, which is horizontal, east and west. And then I define a serial port. And here's the normal setup stuff. This is my screen size. These are the normal kind of things. I actually changed the menu name. I'm starting my robot in the middle of the screen, and then I paint it on there. And now this is something that I don't like, that I know that we can do better. I can do better inside processing. I'm hardwiring it to COM1, which my board is set to. This would be nice if I had some kind of nice selector thing, but I don't know how to do UI stuff yet. And all this does, I won't go through this line by line, but it looks to see if there's a character on the serial port. If there is, it checks to see if it's positive. If it is, it either, if the orientation is this way, it goes in the positive direction. If it's this way, it goes in this direction. If we, or sorry, positive, it goes this way, negative, it goes that way. If we change the orientation and we get a positive, it goes down. If we get negative, it goes up. And if we get an asterisk, we change the orientation. So if I run this, you'll see it. Again, really, really simple. That little blue box is my robot. So here's, I've got my encoder. Oh, sorry. I need to.
John, I have it working.
Do you? I didn't download it. That's why it wasn't running, because I didn't download it on my side.
Can I share it for a second?
Yeah, go ahead. I'm gonna F11 and download too.
Left, right.
There you go.
Button press.
Now, again, ridiculously simple, but the point was to say, hey, if we can get serial from the P2 into processing, we can do stuff. So for example, Chip was talking about yesterday of having a debug mode that doesn't open up one of the cool windows that he normally uses. Well, that means that somebody with some effort could write a program in processing to do something visual with that data that is coming from the debug stream. And you don't even have to wait for the debug stream if you want to do it normal serial like I have. But the point is, you know, somebody asked, hey, can we use processing with the propeller? Of course, it's just serial data. So I just got this from Amazon at lunch. So I've got a book on processing to read once I finish my project with my friend John. And you know, I'm gonna explore it. For those that are running in other operating systems and maybe using Eric Smith's compiler or something else, you know, it's still, you can send serial, and, you know, processing is cross-platform. In fact, one of the folks that responded to Ken's challenge wrote, apparently processing can do Python now, which I didn't know. I kind of like, because I prefer Python to C, so I'm gonna have to look at that. But it is it's a tool to use. Send serial out of the propeller, use processing to do something interesting with it. Somebody just said they had a question for me, so please feel free to ask.
Yeah, there are a couple that are stacked up.
Oh, okay. Yeah, please. I'll stop talking. I've presented everything.
What if you have more encoders than smartpins? Are there any clever ways to extend the capability?
That's a lot of encoders. So what I would do, to be honest, is I would, if you really had that many encoders, I would use a P2 on a slave board to monitor all the encoders and then send serial messages back to the master encoder to deal with that. Because you're going to need some external hardware anyway. So you might as well just do it smart. That way you can have a nice messaging. So that's why, you know, I was talking about that. I thought I had it here on my desk. The SparkFun encoder, you know, they say, wow, you can have 111 of these things on one I2C bus. And I'm thinking, yeah, it's a lot of load on one I2C bus, and at $20 a crack, that's a lot of money. So if I needed a whole bunch of those, I would put a P2 on there, because then I can get colors and all that other stuff. So yeah, that's one of those cases where there's nothing easy. It's simple, but it might not be easy.
And I think Jim has a question.
Yes, sir.
I don't know if you wanted to type it. Oh.
I'll just ask if that's okay.
Yep.
I wrote an object for the P1 a number of years ago to track the stepper motors on a 3D printer. So I was actually tracking 5, the X, Y, and Z axes plus the 2 extruder motors. And what I was doing was reading or monitoring in assembly the step and direction pins of the stepper controllers. And then basically trying to keep track of the positive and negative steps based on direction.
Sure.
Is there a mode in the smart pins that would allow you to do that, to have one pin read the direction and one pin read the step?
I think there is. I'm going to ask Chip to step in. There is a mode. Again, you know, this is new to everybody, including me. So, but I believe there is a mode that will count transitions on the A pin, and it will either add or subtract based on the position of the B pin.
That's exactly what I need. That's.
I believe that exists. Chip's not chiming in. I'm hoping he's still
Well,
there.
I'm here. Okay, so there's there's a bunch of modes. There's one that's increment on A input positive edge and decrement on B input positive edge. And you can always add inversion to any of those signals with some of those control bits. Also, there's an, let's see, there's.
Well, here's what he wants to do, Chip, just to simplify it. He's got two signals. One is a pulse signal that he wants to count, or he wants to affect a counter, but the direction the counter goes is based on the other signal. So if it's low, make it, you know, decrement the counter. If it's high, but I believe there's a smart pin mode that does that.
Yeah, so if the direction pin, let's say it was high, and that meant a positive step, that would just stay high. And then if you got 1,000 steps on the step pin, or 1,000 transitions, you would then increment 1,000 times. So it's almost like it has to check what pin B is every time it sees a transition on A.
It's smart pin mode 01101. Every time the A pin goes high, B will supply the increment or decrement signal.
There you go.
Okay.
And there's there's all kinds of these counter modes. And let me see, there's a name for that in our documentation. And hey, John, if you want to, you know that one thing you pulled up where you showed the 32-bit configuration value and you showed the A and the B?
Yep.
Can you pull that up, and I'll show you a, I can bring up the filter stuff. There's 3 bits there called F.
I don't think my screen is being shared though, is it?
No, you can share again.
Not anymore.
Let me find my way back to here.
While you do that, John, I'm curious. We're chatting on the chat window about who has demo 04 running. I'm having trouble.
That
Dennis
was the
David does.
Well, I do. Here, let me share, and then I don't need that anymore because we've seen that work.
By the way, that mode that you're asking about, it's called, there's a symbol called PREG up down that will select that mode. It's 01101.
Okay. Yeah, we'll have to look in the, and so I'll figure out, I'll do a little demo of that for next week, and I'll get the nice name of it. Oh, so Dennis, you're saying that you're not getting 4 to work for you? Because that's what I had running when I did, you know, this, because that's the little thing. And just to be, you know, I want to make sure I didn't screw something up, because
it might be me.
I'm having trouble too, Dennis, but David got it running.
All right, so I'm opening it in FlexProp, and I do need to change to Ansi.
Ansi, yeah.
And if I run this, compile and run, so I should get, so it's off now, right? And if I select green, oh, yeah, sorry. The reason why here, I can fix that. What I have WS2812s. You remember we talked about this in detail, and I didn't change that in here. It thinks they're WS2811s. So, oops, where's my?
Yeah, I did that. I had to change that also.
Yeah, because remember the 2811s don't swap the red and the green. The 2812s do. Doggone it, where's my setup? This is where, see, I'm so spoiled with Propeller Tool. It's easy to find these things. So if I change this to 12B.
Mine's working quite well now.
And run again, and press it. So now, if I'm on red, boom, I got red, white, green, Christmas. Now, since Christmas is active, I have to press it again to get out of Christmas. And random. That's not terribly exciting. Twinkle is a little better.
Need to hold it up a little higher, John.
Oh, okay.
Thank you.
Here. That worked. All right. So it is working for me anyway. So the things people talked about, make sure you have your 5 volts on. If you're using a JonnyMac, make sure you got the 5 volts enabled on the side you're using. And you have the correct LEDs, but I'm running the code that is in the, oh, so you're good, Dennis? You're
Yes.
back? All right,
Quite
excellent.
well.
Right on. Okay, since we've been through all of the code demos, are there any other questions? You know, I'm here for everyone.
Hey, John, this is not so much a question, just kind of an observation I found a number of years ago on one of the online forums. I don't know who to give credit to because it was about 10 years ago. But you know how we use the rotary encoder to pick up the 2 signals that are offset by 90 degrees?
Mm-hmm.
You can take some little Hall effect sensors for picking up magnetic fields. And I think the guy that posted about it said he found it on a refrigerator magnet. But the way those kind of magnets go through the machines, they're magnetized in an alternating north and south pole along their surface. So you can actually use that, and you have to get like a PC board built with just the right spacing so that while one magnet is, they have to be basically 50% off, so that as they go through the fields, they'll give you the same signal that a rotary encoder will give you.
Oh, interesting.
So you can very easily create a nice linear position sensor with that. Now, one of the problems is most of the magnetic tapes that you can buy, the way they come off the machine, the pattern is the wrong direction. So you have to kind of search around to find something that has a wide enough pattern that'll give you whatever type of length that you're trying to shoot for. But it can also be used to put around maybe a shaft if it's large enough, and just glue that tape there so you get a real high resolution signal off of like a shaft of a motor or some other spinning object.
Yeah, there's a variety of mechanisms for getting that signal. Again, it's just 2 square waves that are offset by 90 degrees. You see, you know, for example, again, in the high quality encoders, I'm not sure what's in here. I know it's optical. So there could be, it could be a reflective thing. You see that sometimes where you have reflective sensors, or there could be, you know, an interrupt sensor as well, where you have, you know, you have a disc with a bunch of vanes in it, and then you have 2 sensors that are offset. And so that creates the thing. And like you said, there are a variety of magnetic sensors that do this kind of output. There's a bunch of it. The neat thing is, again, from our standpoint electrically, it's a really simple set of signals. And, you know, now, you know, we have lots of options. We can deal with it in code, or, you know, the smartpins, you know, handle it for us. So that's what I'm doing with P2s. I went through today's exercise, and it did go longer than I hoped, but I hope you enjoyed it. The point was, as I said, I will always strive to give you the whys behind the hows. You know, if I hand you something and don't teach you, and then I'm saying generically to anybody, how to use it, I think I've done a disservice. So with all of my code, and that's why I'm continually asking if you have questions. Now, that you don't, I'm taking on, you're just shy. You're not like me, who would just talk to anybody. But you know, if you have questions, my email is in all of the code. I do try to spend a bit of time in the forums each day, so you can reach me there. as I do enjoy doing this stuff. I mean, I have tough days too, like everybody else, as far as with coding. Sometimes I get frazzled, but more often than not, I'm having a great time and smiling, and I want more people to be able to participate in that. And I got the indication, like I said, I got some incredibly kind notes last week, and I'm so grateful for that. And where people are you know, the kind of the content of the message was, hey, you know, now I feel like I can do it too. And that's what I want. I want anybody who wants to try to do embedded programming to be able to do it. And you can see, it doesn't matter age. You know, I'm 58 years old. Kevin is 10. There's a long span of years between us, and yet we both have this same love for embedded microcontrollers and robots and those kind of things, and having fun along the way.
John, I want to give you a tremendous thank you. I learned a lot today and look forward to going back through this before next week.
That is the case.
The challenge.
Yeah. Try the challenge and then go back and look at the presentation. You know, I had a boss one time named Bob, a really nice guy. He said, you know, humans have to hear things 5 to 7 times before it sinks in. Now with us and the ability to experiment, that helps the sink in part. So I will encourage people to, you know, you've got a zip file, so you've got the original file stored safely, or I'll give them to you again, you know, go into them and modify them and change them. Now, again, the crazy side of me will say, if you modify my programs, please follow my style. You know, do them neatly, you know, follow the rules, and, you know, just have fun.
And John, if I could add one more thing.
Yeah.
So at present, all these wonderful gems that are getting produced are scattered all over the place. They're on the forums, they're deep in YouTube videos, they're sometimes source code downloads on product pages or on the OBEX. But we're working towards creating something called Quick Bites that will take these pieces and provide it'll be like a living, breathing OBEX. It'll include the source code, a description, any pictures that went with it, and hopefully links to excerpts of videos.
Oh, good.
And any hardware that went with it as well. So we're just setting up a template inside Parallax right now so we can start to produce more useful examples for people that wander in, and we don't have to say, go look at 240 hours of video.
Right. Well, that's the thing too. You're trying to take these things. I mean, today was, you know, a bit, and next week we'll do, you know, more things, but it's, you know, one thing at a time. So we're kind of building, not only building code libraries, but building a library of knowledge within ourselves. So I hope now that anybody who hadn't previously used Quadrature encoders now feels like, okay, I've got the tools. And importantly, you know, put it to use, give it a try. Especially if you've got the kit or you ordered one from Amazon or whatever, give it a try. You know, do something that you want to do with it, because that will lock in the real understanding.
Great.
Oh.
And for Carol's problem, we'll send her a few prop plugs second day on Monday.
Okay.
If she does a little more troubleshooting
really
and swaps cables and things.
Yeah, we've been doing that all during. I've been listening to John, but all during it.
Well,
Bill's on his computer and I'm on my other computer, trying to get this thing to work.
I'll look up to find out what I did to get mine working. I actually opened a ticket with support, your support people, and worked with them for a while on it, so they may have some details as well. But I'll see if I can find the emails that I had from both Parallax and wherever the company who manufactures the chip is. I talked to both of them. And
FTDI.
Details. So,
one interesting thing is we've tried out many different cords, and I have 2 of the prop plugs. Neither one work, which to me is very unusual. I wouldn't think they would both not work unless there's something I'm doing wrong somewhere.
yeah, I was trying to get a Propeller 1 Board of Education working, and I was having trouble with it. And as I said, I went and reinstalled the drivers, and then I had to immediately plug in the USB cable with the P1 attached to it and power it up, and that was what cleared it up.
Okay, I've never had a problem with the P1, so.
But this is to get the driver working, because I was also trying to
Bill just
sure
brought up
where.
a question that I didn't
What?
notice. I'm sorry. What are the dip switches up in the corner of the edge board?
Those select your boot mode. So, and you asked why didn't we put the USB on the edge, or why do we have to have a prop plug?
Yeah.
It's because we wanted to leave all the options open, you know, because you really only need serial at 3.3 volt CMOS levels to talk to this thing. And
Mhm.
USB kind of it'll hog up all those connections, and then you're stuck with only USB. You can't do anything different. So we wanted to make the board, you know, uncommitted in that way. And those dip switches, let me put my glasses on.
Me too.
So the first one controls whether the LEDs are enabled or not. The second one connects the flash chip. So if you have that second one off, it'll never boot from flash because it won't see the flash chip. And then the last two pull P59 up or down to force it to use the flash or force it to use serial.
Or should they be?
Okay. Are those, I suppose they are, I haven't really looked yet. Are those covered thoroughly in the documentation for the edge?
I believe they are.
Yeah, I believe so too.
Yeah.
That depends on what you're doing, Bill. Bill asked what position they should be in. But that depends on what you're doing.
Yeah, see, we didn't, without the USB being stuck on here and just having these logic signals available, you can devise all kinds of your own loaders. You know, you're not stuck using a PC and any kind of virtual serial port driver. You can use another P2 to load a P2 or another P1 or whatever you've got. And you could load up multiple edges simultaneously. There's a lot of stuff you could do that you couldn't do if we just stuck it with USB. And we don't have the quiescent current draw that USB would cause. So you can program it with a Prop 2 plug and unplug that Prop 2 plug, and you're suffering no, you know, current expenditure because you have the USB chip sitting there all the time.
Don't break my board. I'm sorry. It's difficult sometimes for me to let Bill play with my stuff.
What is the difference between the old prop plug and the new one?
I don't know that there is any
Micro USB.
Yeah.
Yeah,
Yeah, the
that's it.
connector is different. It's the same chip though, isn't it?
I believe so. It's something that works just the same for our purposes.
But the old one works perfectly well on the JonnyMac board.
Yeah, it does. I use it at first.
Yeah, I'm using one that I bought like in 2010.
Oh wait, how old? Because I've got the early green ones from the P1, and then I've got a blue one, which was for P2, and then I've got the two that have no real color except what the circuit board is that came with the JonnyMac board.
I think those changes had to do with the way the FTDI chip and the multiple COM port remuneration problem.
I have a Rev A prop plug.
Yeah, I think the new one prevents thousands of ports from getting created.
Yeah, I have a Rev A and it works fine on the.
Yeah, I have an old one that's working fine too.
Okay, let me look.
Well, Carol,
You just have to plug it in upside down on the edge breadboard.
Well, the pins will be the same if I put VSS and VSS.
Yeah, yep.
Right.
Yeah, but I was just saying orientation wise.
That's what I look at rather than
an older prop
down.
plug like this. You plug it in upside down on the JonnyMac.
Yeah.
Well, as she continues to work through this over the weekend, she'll mail me on Sunday night, and we'll know for sure that she's got an issue. And on Monday, I can second day her a couple prop plugs, so she's ready to go by Wednesday.
Did you try it on a Prop 1 with another computer and see if it actually works?
The new plug, the little flat plugs.
But did you try it? Have you tried it like maybe on a Prop 1 board on a different computer?
No.
To verify that the plug works?